Welcome to Holyfield Physics TV. I'm going to look today at the life cycle of stars, and this is for the A2 Cosmology unit. All stars begin life in a huge cloud of dust and gas, many light years across. Apologies for the poor graphics here. What we'll have is that some regions of the gas will be more dense than others, so have a greater gravitational pull. And these regions naturally pull in the dust and gas from the rest of the cloud. It's a bit of a positive feedback effect. As the cloud collapses in on itself under its own gravity, all the dust and gas accelerate towards the centre. And this increase in kinetic energy, this change of gravitational potential to kinetic energy, raises the temperature. Provided the sun, the star, is large enough, the core becomes hot enough and fusion begins. This is the birth of the star. The hydrogen is fused into helium, and this releases vast amounts of energy. Gravity is still trying to squash it down, but the radiation pressure that's now produced balances this out, and we have a stable star, or what's called a main sequence star. We've got many different sizes of main sequence star. We've got the giant hot blue stars. They only live for a few million years. We've got small cool orange ones, and they will live, well, pretty much for the whole of eternity. And then we have medium-sized stars, yellow ones like the sun, that will live around about 10 billion years. One would think that the larger the star, the longer it will live, but because of the huge amounts of gravity involved here, the larger stars, the ones with more mass, actually need to burn their fuel at a much faster rate to balance out the gravity, and that's why they don't live quite as long. Well, when the hydrogen runs out, what happens to them now depends solely on their mass. Sun-sized stars follow one route, and stars larger than 1.4 solar masses follow another. This 1.4 solar mass is called the Chandrasekhar limit, and it's the cutoff point between supernova, white dwarf. So if we look at sun-sized stars, the core collapses in on itself under its own gravity once the hydrogen's run out. It gets hotter, but it doesn't get hot enough to fuse helium. The outer atmosphere expands and cools down, and so we get a red giant. This is the ultimate fate of our sun. And there you can see Mercury, Venus and Earth, and it's most likely that Mercury and Venus will actually be swallowed up by the sun, and the Earth at that distance from such a large star will fry to a cinder. The oceans will evaporate, as will the atmosphere. After some time, the atmosphere of the red giant dissipates away, and all we're left with is an extremely small, extremely hot white dwarf, which will cool and become a red dwarf. And eventually, it will cool so much that it will become a black dwarf. In essence, our sun will simply fade away from view. With the bigger stars, once the hydrogen is used up, the core still collapses and gets hotter, and the atmosphere expands just as before. But this time, the core becomes hot enough to fuse helium. The sort of temperatures we're talking about here, 10 to the 8, 10 to the 9 Kelvin. The helium runs out and we go through successive stages of contraction and fusion, heavier and heavier elements. This is a red supergiant star, a bit like Betelgeuse if you look up at Orion, Betelgeuse is so large that it would fit the inner 4 planets plus Jupiter inside it. It's enormous. Finally, we get to a core that's made of pure iron. When we get to pure iron, it doesn't matter how hot the core gets, it won't be able to fuse it into anything heavier. Gravity takes over and crushes down the core very rapidly, but it suddenly stops and sends a shockwave that blows the star apart. And this is what we call a supernova explosion. Supernovas will give out more light than 100 billion stars, more than an entire galaxy, but they eventually fade from view, and the ultra-dense core which is left behind is either going to be a neutron star or a black hole. Small thought for you. Gamow showed that the Big Bang could only produce hydrogen and helium, maybe a little bit of lithium as well. About 79% hydrogen, about 21% helium. But everything that we know of is made up of heavier atoms: carbon, oxygen, iron, gold, calcium. All of these elements, the only place they could possibly be produced is in stars, and then recycled by supernova explosions to form new stars and new solar systems, and eventually beings like us. Yep, we're made of stardust. This has been Holyfield Physics TV. I'm Richard Gould. Thanks very much for watching and listening. Work hard, do well in your exams.